Imagine an object with a density so incredible and gravity so powerful that even light, the fastest messenger in the universe, becomes trapped, unable to escape its immense pull. This is the world of black holes, a place where space itself is warped beyond recognition. According to Einstein's theory of relativity, when enough matter is squeezed into a sufficiently small volume, a black hole is formed. Its boundary is known as the event horizon. Once you cross it, there is no coming back. The larger the black hole, the more matter you need to compress. Yet, even an object as massive as our Sun would have to be crushed down to a mere 3 kilometers to reach that point. At that size, its density would be absurdly high, far exceeding anything we observe elsewhere in the modern universe. For objects with less mass than the Sun, invisible forces between subatomic particles act as a structural support, preventing them from collapsing into black holes. Tonight, we continue our exploration of the cosmos to understand the physics behind these dark giants. It is a long story, so let us begin our journey into the mechanics of the void. Not all stars are destined to become black holes. Our Sun, for example, lacks the necessary mass. However, stars more than 10 times the mass of the Sun are likely to follow that path. It is estimated that in our Milky Way galaxy alone, there could be over 1 billion stellar mass black holes, though most remain invisible unless they are part of a binary system where we can detect them through their gravitational influence on a companion star. Beyond these are intermediate mass black holes, potentially formed from stars over 100 times more massive than the Sun. These massive stars may leave behind remnants during their oxygen-burning phase, possibly even linking them to the production of gamma-ray bursts. Then there are the supermassive black holes, behemoths with masses ranging from millions to billions of suns. These are believed to reside at the centers of galaxies. At the heart of our own Milky Way lurks a black hole with the mass of 4 million suns. Even more extreme are quasars, incredibly bright beacons in the distant universe powered by supermassive black holes, some weighing as much as 100 million suns. From stellar to supermassive, these black holes typically have radii larger than a kilometer and are considered macroscopic objects, governed by classical physics where quantum effects are largely negligible. However, there is another fascinating category: primordial black holes. These are thought to have formed in the extreme environments of the early universe, mere milliseconds after the Big Bang. Because the average density of the universe was so high then, these black holes could be much smaller than stellar mass ones. Those formed slightly later might still be macroscopic, such as those created 1 second after the Big Bang with masses comparable to supermassive black holes but on the smaller end. A primordial black hole with the mass of the Moon could be microscopic, perhaps only the size of a micrometer. Yet, even at that scale, they could produce significant astrophysical effects or provide clues to the mystery of dark matter. If a black hole's mass falls below a certain threshold, roughly the mass of a mountain or 10 to the 12th kilograms, its size shrinks to smaller than a proton. This is where things become truly strange. In 1974, Stephen Hawking discovered that black holes do not just swallow matter, they also radiate energy. The smaller the black hole, the higher its temperature. For a mountain mass black hole, the temperature would be a staggering 10 to the 12th Kelvin, radiating particles like photons, electrons, and positrons. As it radiates, it loses mass and becomes unstable. The smaller it gets, the hotter it becomes and the faster it shrinks. When the mass drops to about 1 million kilograms, the process ends in a violent explosion, releasing energy equivalent to 1 million megaton nuclear bomb in just 1 second. The time required for a black hole to evaporate completely depends on its initial mass. A black hole with the mass of the Sun would take an incredibly long time to evaporate, roughly 10 to the 64th years. In contrast, a black hole of 10 to the 12th kilograms has an evaporation time of about 10 billion years, which is roughly the age of the universe. This means primordial black holes of this specific mass range are evaporating right now, while smaller ones vanished long ago. We call these smaller black holes quantum black holes because quantum effects play a decisive role in their behavior. Hawking's work was a major breakthrough because it linked three fundamental pillars of physics: general relativity, quantum theory, and thermodynamics. However, that was only the first step toward a complete theory of quantum gravity. When matter density reaches the Planck density, roughly 10 to the 97th kilograms per cubic meter, classical analysis fails. At this point, gravity is so strong that the quantum effects of space-time must be considered to understand the formation and evaporation of Planck-scale quantum black holes. Such a theory might even predict that black holes leave behind tiny, stable Planck mass remnants after they evaporate. In more recent years, an intriguing possibility has been proposed: the existence of extra dimensions might play a key role when black holes shrink to the Planck scale. These extra dimensions would significantly alter our understanding of gravity at extremely small distances, perhaps providing new clues for how quantum gravity operates. The concept of extra dimensions dates back to the 1920s, when Kaluza and Klein suggested that a compact fifth dimension could unify gravity with electromagnetism. Later, with the discovery of more subatomic forces, superstring theory introduced 6 extra dimensions, and M-theory unified various string versions by predicting 7. Usually, these dimensions are thought to be so small that they have no observable effect even at the Planck scale for black holes larger than the Planck mass. However, in certain models, these dimensions might be larger, making gravity much stronger at short distances and causing it to deviate from the standard inverse square law. Some models even propose warped extra dimensions with similar effects, where gravity becomes significantly enhanced at microscopic scales. When an evaporating black hole shrinks to the Planck scale about 10 to the minus 35th meters and 10 to the minus 8th kilograms, it becomes what we call a Planck quantum black hole. It is far smaller than any fundamental particle but much heavier. This is likely the smallest possible black hole, as space itself can no longer be viewed as continuous below the Planck length. It is also possible that many primordial black holes formed due to quantum fluctuations during the Planck epoch, though they would have evaporated almost instantly. The idea that gravity becomes stronger at small scales leads to an exciting possibility: black holes might be created in particle accelerators like the Large Hadron Collider. These machines accelerate particles like protons to near the speed of light, giving them immense kinetic energy. In the LHC, a proton can reach 7 tera-electron-volts, concentrated in a tiny volume during a collision. Without large extra dimensions, the chance of creating a black hole is nearly zero, as the energy density required, the Planck density, is far beyond the LHC's reach. However, if extra dimensions exist and lower the Planck scale, the energy needed might fall within the range of our current technology. Such a black hole would be as small as a fundamental particle and would evaporate almost instantly, lighting up particle detectors like a Christmas tree. While there is no experimental evidence yet, this opens a door to exploring the structure of space-time and hidden higher dimensions. Understanding this requires reconciling a profound paradox highlighted by Hawking's discovery, the conflict between general relativity and quantum mechanics. Relativity suggests information falling into a black hole is lost forever, while quantum mechanics insists information must be preserved. Whether black holes leave behind stable remnants to store this information remains one of the greatest questions in modern physics. Ultimately, black holes represent the ultimate laboratory for the laws of nature. From the collapse of massive stars 40 times the size of the Sun to the supermassive giants at the heart of galaxies, these objects define the boundaries of our knowledge. In the early universe, primordial black holes may have formed from density fluctuations, potentially contributing to the mysterious dark matter that holds galaxies together. Even though the first solution describing a black hole was found by Karl Schwarzschild in 1916, just months after Einstein published his general relativity, it took decades to realize the full physical implications of his work. Today, we continue to use those same vacuum solutions to describe the non-rotating, spherically symmetric space around these dark stars, forever chasing a deeper understanding of the bridge between the very large and the very small. Far from the massive center of a black hole, the behavior of space-time remains nearly flat and predictable. However, as we approach the core, we encounter specific points where our classical descriptions fail. While some of these boundaries, like the event horizon, are merely mathematical artifacts that can be resolved by changing our coordinate systems, the true singularity at the center is a different story. At this zero-point radius, the curvature of space-time becomes infinite. This extreme curvature dictates the movement of all particles and light. In the familiar flat space of our daily lives, light travels along paths we call light cones, which represent the ultimate speed limit of the universe. But near a black hole, these light cones begin to tip and tilt due to the intense gravitational pull. As we reach the Schwarzschild radius, the event horizon, the light cones tilt so severely that every possible future path points inward. Once you cross this invisible line, even light is forced toward the center, making escape physically impossible. This leads us to the famous no-hair theorem in general relativity. It suggests that regardless of how a black hole was formed, its entire external identity is stripped down to just 3 measurable parameters: its mass, its electric charge, and its angular momentum. From the outside, all other details, the shape, composition, or history of the original object, are lost forever. In the eyes of the universe, The black hole has no hair. It is an incredibly simple object defined only by its most fundamental physical properties. The mass of a black hole also determines its temperature and how it interacts with the quantum world. Large black holes behave more like classical objects, emitting Hawking radiation and slowly decaying over vast time scales. However, as we move toward the incredibly tiny Planck scale, we encounter quantum black holes that no longer emit steady thermal radiation but instead decay by producing a few high-energy particles. Theoretical physics suggests that high-energy particle collisions could, in principle, create these tiny black holes through intense shockwave interactions. When these collisions occur under specific conditions, they form what researchers call closed trapped surfaces, which are the telltale signs of a black hole's birth. To truly grasp this process, we need the support of quantum gravity theory. In recent decades, a major shift in thinking has occurred. We once thought the characteristic scale of quantum gravity was unimaginably high, but new models involving extra dimensions suggest it might be much lower, perhaps within the reach of our current particle accelerators. In these large extra-dimension models, gravity is allowed to spread out into hidden spatial dimensions, which explains why it feels so weak in our three-dimensional world. By adjusting the size of these hidden dimensions, the energy required to see quantum gravitational effects, including the creation of many black holes, could be pushed down to the tera-electron-volt range, making the study of the early universe's most violent events a possibility in a laboratory setting. Rather than trying to create many black holes directly, some physicists use a method called effective field theory to study quantum gravity indirectly at lower energies. This approach allows us to account for high-energy effects by looking at how particles like the Higgs boson interact with the curvature of space-time. These interactions are governed by specific parameters that link gravity to the expansion of the universe. While current experiments provide some constraints, we still lack the precision to see the full picture of quantum gravity. For example, certain theories regarding cosmic inflation require these parameters to take very specific values that our current technology cannot yet reach. This indirect path is invaluable because, in theory, these values can be calculated from a more fundamental theory of quantum gravity, offering us a rare glimpse into a realm that is otherwise hidden. Furthermore, these Planck scale effects might influence how the fundamental forces of nature unify at extremely high energies. Without accounting for quantum gravity, our predictions about the unification of electromagnetism and the nuclear forces might be incomplete or even incorrect. When we look back at the very beginning of time, specifically the inflationary period of the early universe, quantum gravity becomes essential. The universe likely underwent a rapid expansion driven by a scalar field. In this high-energy environment, quantum black holes and their associated effects could have played a significant role. While these effects might explain some features of our astronomical data, they could also potentially destabilize the process of inflation itself. To solve such paradoxes, some propose that black holes might leave behind stable remnants that store information in an incredibly small volume, potentially resolving the long-standing black hole information paradox. However, Observing these tiny remnants or creating them requires energies far beyond what we can currently produce unless hidden dimensions or new particles exist. Even if we cannot see them directly, these quantum black holes might exist as virtual particles, influencing the results of low-energy experiments through a massive number of potential quantum states. If the number of these states is quantized according to the Planck scale, their impact remains controllable and does not disrupt our current understanding of low-energy physics. Ultimately, the marriage of general relativity and quantum mechanics suggests the existence of a fundamental minimum length in nature, often referred to as the Planck length. This means there is a limit to how small we can measure. Below this threshold, the very concepts of distance and space lose their traditional meaning. This conclusion arises when we combine the uncertainty principle from quantum mechanics with the gravitational collapse described by relativity. If you try to measure a position with extreme precision, you need a probe with incredibly high energy and a short wavelength. However, once that energy is concentrated into a space smaller than the Planck length, it triggers the formation of a tiny black hole, which effectively hides any further detail. Thus, gravity itself sets a universal limit on our ability to resolve the smallest scales of reality. Whether we think of this as space-time foam or discrete steps in a string theory landscape, it indicates that our universe has a built-in resolution limit. Even if we use highly sensitive tools like interferometers, the dual constraints of quantum uncertainty and gravitational collapse prevent us from ever reaching infinite precision. As we ponder a free particle being measured twice over a period of time, we are reminded that at the most fundamental level, the universe is not a continuous void but a complex tapestry with a definitive, tiny grain. The uncertainty principle tells us that the more precisely we try to measure a particle's position, the more we disturb its momentum. When we apply this to the extreme gravity of a black hole, we discover a fundamental floor to reality, the Planck length. To measure anything smaller than this scale, you would need a probe so energetic and massive that the measurement apparatus itself would collapse into a black hole before the result could ever be transmitted. This implies that space-time may not be a smooth, infinite continuum, but rather a structure with a finite number of degrees of freedom, a cosmic limit on the amount of information any given region of space can hold. By treating the Planck length as a natural cutoff, physicists can resolve the mathematical infinities that usually plague quantum gravity calculations. This self-healing mechanism of gravity suggests that as we pump more energy into a system, instead of seeing smaller details, we simply create larger black holes, a process known as classicalization. In this regime, even our basic notions of cause and effect might break down, leading to non-causal signatures where events appear to occur outside their normal chronological order near the Planck scale. Beyond the simple models, black holes come in various exotic species. There are Kerr black holes, which spin so rapidly they drag the very fabric of space around them in a whirlpool-like effect known as frame dragging. In these rotating systems, the vacuum fluctuations near the event horizon are twisted, potentially allowing particles to tunnel out and escape through purely quantum processes. Then there are Reissner-Nordstrom black holes, which carry an electric charge, creating a complex interplay between gravitational and electromagnetic forces. In higher dimensional theories like string theory, we even encounter black strings and black membranes that stretch across hidden dimensions. To study these unreachable giants, scientists have turned to black hole analogs in the lab using sound waves in fluids or light in specialized materials to recreate the physics of an event horizon. These experiments have already detected hints of Hawking radiation, proving that the boundary between a black hole and the rest of the universe is a place of active, quantum creation rather than just a silent grave. The most transformative moment in this history arrived in 1974, when Stephen Hawking shattered the image of the black hole as a cosmic vacuum cleaner. By applying quantum field theory to the curved space around a black hole, he showed that the vacuum is never truly empty. It is a bubbling sea of virtual particle-antiparticle pairs. Near the event horizon, the immense tidal forces of gravity can rip these pairs apart before they can annihilate. If one particle falls in while the other escapes, the black hole effectively emits radiation. Because of the law of conservation of energy, the black hole must lose a tiny bit of its own mass to pay for the particle that escaped. Over unimaginable eons, black holes do not just sit there, they evaporate, shrink, and eventually vanish in a final, brilliant burst of energy. This discovery gave birth to the field of black hole thermodynamics, linking the cold geometry of general relativity to the warm, statistical world of heat and entropy. It tells us that a black hole's surface area is actually a measure of its entropy, the total information it contains. As we look toward the future of physics, theories like loop quantum gravity suggest that the singularity at the heart of a black hole might not be a point of infinite density at all, but a dense, discrete transition of quantum threads. Whether they are the remnants of the early universe or the engines of distant quasars, black holes remain the ultimate bridge between the very large and the very small. That concludes our exploration for today. May your dreams be as vast as the cosmos. We'll see you in the next episode.